Hi everyone. In today's video, we are going to look at the cross-NOR flip-flop. And the cross-NOR flip-flop is made with two NOR gates. I'm just going to draw the circuit here. And the interesting thing is we have two inputs, so S and R, and we have two outputs, Q bar and Q. The other input to these NOR gates is actually a little feedback from the other NOR gate. So that presents an interesting situation because the input to each of these OR gates is actually an output from the other OR gate. So that seems like a bit of an impossible situation. But it's not impossible if we remember how NOR gates work and look at the truth table for a NOR gate. So if a NOR gate has two inputs A and B and an output Y, we could have 0, 0, 0, 1, 1, 0, or 1, 1. For an OR gate, the only time we'll get a 1 is if both inputs are 0. Otherwise, we're going to get zeros. So basically, anytime the input is 1, we will get a 0 for an output, okay? And so now we're going to analyze this circuit for the four possible combinations of the input, and we're going to build a little truth table for that. So looking at this cross-NOR SR flip-flop, it has two inputs, S and R, and that stands for set and reset, okay? And we have, I'll just put a double bar there to separate inputs and outputs. We have two outputs. We have Q, and notice that's Q here on the bottom, but I'll write it first here in the truth table, Q and Q bar. And the reason that they're written like that is we are expecting these two outputs to be the opposite of each other, okay? And so we could have 0, 0. I'm going to write 1, 0 first, and then 0, 1, and then 1, 1. Okay, and I'll explain my reasoning for doing that. It doesn't actually matter which order you put this in, as long as you've covered all four possible combinations. So let's look at this combination right here, where S is 1 and R is 0, and we call this, I'm just shortening a line here, we call, oops, and now I'm over erasing. We call this when S is 1 and R is 0, we call this the set condition. So that's called the set condition. So with the set input high and the reset input low, we're calling that a set condition. So S is equal to 1, R is equal to 0. Now those other inputs to the NOR gates, they depend on what the output of the previous of the other NOR gate is, and that seems impossible to solve until we remember that looking down here in the truth table, anytime one of the inputs to a NOR gate is 1, it doesn't matter what the other input is, the output will automatically be 0. So for this top NOR gate, automatically that output is 0. And then that 0 feeds back here to this input as 0, and 0, 0 makes a 1. So we have the condition, and I'm going to put the outputs in my table here, where Q is 1 and Q bar is 0, and that's our set condition. So we're saying that Q has been set to 1, okay? So let me erase those numbers from my diagram, and we'll look at another situation. Okay, so let's go back to the table and we'll look at this combination here where S is 0 and R is 1, and this is called our reset condition. So S is 0, R is 1. And again, anytime the input, any input to a NOR gate is 1, that's going to drive that output to 0. And then that 0 is going to feed back to this input, creating an output 1 here. So we see that the reset condition makes Q go to 0, and then Q bar is the opposite, which is 1. Let's look at this interesting case where S and R are both set to 0. So this case here, if S and R are both set to 0, we call this a no change condition, and I'm going to explain why. No change. When S is 0 and R is 0, we don't know specifically an exact value for Q and Q bar, right? Because now we're looking at this part of our NOR gate truth table, and or this part or this part, right, where one of our inputs is 0. And the thing is, if the other input is also 0, we'll get a 1. But if the other input is a 1, we'll get a 0. And so if you look at that behavior, the output is going to be the opposite of whatever that other input is. Okay, so you know, theoretically, when we look at this, we say, well, right now this output is sitting at something Q, we don't know what it is, and this output is sitting at something Q bar, and we don't know what it is. But we know that if this Q gets fed back to this input, the output will be the opposite of Q, which it is. And if this Q bar gets fed back to this input, the output will be the opposite of that, which it is. So we can see that there's actually been no change to the circuit. And so when we write that in the truth table, we write Q stays as Q and Q bar stays as Q bar, and that's indicating no change. But we don't know whether Q is 0 or 1, and that would depend on what was the value of Q when we put the circuit into the 0, 0 input state. So to look at this with some numbers in there, let's erase these and imagine that when I flipped the switches for S and R to 0, that Q was already sitting at 1 and Q bar was already sitting at 0. Well, this 1 being fed back here would create a 0 output, which it already is, and this 0 fed back here would create a 1 output, which it already is. So no change to the circuit. If I change my starting conditions and I say, okay, what if Q was 0 and Q bar was 1? Well, in that condition, this 0 being fed back would cause a 1, which it already is, and this 1 being fed back to here would cause a 0, which it already is. So again, it's no change, right? So whatever the values that Q and Q bar had at that point, if we put the inputs to S of S and R to 0, there's going to be no change in the output. So that's sort of a holding condition that we have. We call it the no change condition. The last condition for our truth table is when S and R are both 1. I do that in yellow. So looking at this condition here, we call this condition a few names. We call it invalid, illegal, or not used. And I'll show you why. If S and R are both 1, we know that that is going to drive automatically the outputs to 0 and 0. Because anytime an OR gate input is 1, the output becomes 0. That puts our outputs in a state where they are actually not the opposite of each other, right? Q and Q bar should be the opposite of each other, and they're not. So we don't want to use this input condition, and that's why we call it invalid and not used, and we just avoid it in the circuit operation. Okay, so that's the Krosnoer SR flip-flop.